Hello, my name's Jeff Messier. I'm a professor in electrical and computer engineering in the Schulich School of Engineering at the University of Calgary. And this is Module 12 in my Computer Networks lecture series, where I introduce at a high level the idea of how to design a protocol for accessing a shared channel. So if you've been following these videos in order, you'll know that in the last few modules we've really been diving down into the details. So we've been talking a lot about error detection mechanisms, how they work and perform, ARQ algorithms, how they work and perform, and right now is a good time to sort of take a step back and reorient ourselves and remind ourselves of where we are exactly in the protocol stack. Because again, I'm going to use the structure of the protocol stack to essentially guide the high-level structure of this lecture series. And so here is a picture of the protocol stack running on a series of nodes. And again, as a node could be a computer, a smartphone, wireless thermometer or wireless thermostat in your home. And all of these nodes are communicating together over a shared channel. And so we've talked about the physical layer and how the physical layer basically takes digital information, ones and zeros, converts the ones and zeros into analog waveforms that can travel over this shared analog channel. And this could be a wire. It could also be a wireless channel, so wireless transmission within a certain area. Our focus currently is on the data link layer. So we call this, so if the physical layer is layer 1 of the protocol stack, the data link layer is, logically, I guess, layer 2. And up until now, we've been really focusing on the logical link control sublayer within the data link layer. And conceptually, at least, the purpose of the logical link control layer, or LLC, is to make the error-prone physical layer appear magically like it's error-free. And we know that the physical layer has a certain raw data rate and a certain probability of bit error. And the way the logical link control layer sort of cleans up these errors is by introducing error detection into the frames that are transmitted over the analog channel that allow us to spot when an error has occurred in a frame, and then also implementing an ARQ algorithm that retransmits bad frames. And so essentially, the logical link control layer refuses to pass a bad frame up the protocol stack and will keep asking for retransmissions over and over again until the frame gets through. And the penalty, of course, for this is a lower effective throughput, right? Because we're kind of wasting time or we're stealing channel bandwidth to resend frames that have already been transmitted. And we now know how to put some math around that to determine sort of our average effective throughput. Just a reminder that ARQ algorithms, while we introduce them at the logical link control layer as part of the OSI protocol stack model, ARQ appears at a lot of different layers in the protocol stack. When you look in detail at the Wi-Fi protocol stack, for example, they will say that ARQ is actually built into part of the medium access control layer. We also see ARQ up at the transport layer when we look at TCP. So ARQ actually happens a number of places. And remember, the OSI protocol stack model is just that. It's a model, a general guideline. When people build specific protocols, often they will deviate from that guideline. And so now, having looked at the physical layer, looked at the logical link control layer, we're now going to talk about the medium access control layer. And the purpose of the medium access control layer, or MAC as we most commonly call it, is to help manage the challenge of having multiple nodes access a shared channel. So, as I suggested, the purpose of the MAC sublayer is to facilitate or allow many nodes to communicate over a shared channel. Now, I should be very specific at this point and define what I mean by shared channel. A shared channel is when we have more than 2 nodes, so 3 or more nodes, accessing a channel where any node can transmit directly to any other node. So this is different than a multi-hop channel over a mesh network. And so we've introduced the mesh network architecture where we have, several nodes. And if this is the source node, this is the destination node. The source node maybe transmits to an intermediate router. The router can choose one of 2 paths to the destination. So we're not talking about this multi-hop scenario yet. We get to that later on. So for now, we're talking about a situation where each node can transmit directly to any other node without having to go through an intermediate hop or an intermediate device. This should be 2, this should be N, that's a little typo. And so I guess the original kind of classic example of the shared channel was old Ethernet networks. So back when I was, a graduate student back in the day, I was just seeing the tail end of 10BASE-T Ethernet. And that was actually where all Ethernet cards connected to a shared coaxial cable using those little BNC T connectors, like maybe some of you have used for, undergraduate oscilloscopes, low range oscilloscopes. And all Ethernet cards were connected to a common coaxial cable, and any Ethernet card could communicate directly to any other Ethernet card. So that's a shared channel. Also, every Ethernet card heard everybody else's transmission, and that's kind of a byproduct of that setup. As we're going to see as we discuss Ethernet in more detail later on, modern Ethernet doesn't work like this anymore. And so really the most relevant shared channel for us these days is the wireless channel. Obviously, Wi-Fi, cellular communications, low-speed instrumentation wireless is huge. Wireless is just a fundamental part of our lives. And the wireless channel is truly shared. So if node 1 wants to transmit to node N, it can. But of course, because of the broadcast nature of the wireless channel, node 2 will overhear the transmission of node 1 to node N. Is this an unusual scenario? It's really not, because when we talk about a shared channel, the example that we have from everyday life is just sort of our shared conversation channel or our audio channel when we have conversations with multiple people. So in a classroom, when an instructor is speaking to a group of students, or when you're in a house with some friends and you've got maybe 4 people together having a conversation, that is the classic shared channel. When one person says something, everybody else can hear it, even if the comment is not necessarily for them. And we use kind of an unspoken protocol that we all sort of learn growing up regarding how to manage a conversation. So we have, sort of politeness rules, I guess, right? So things like, don't interrupt, wait for the person to talk before you talk. Maybe at a higher level, if a conversation's been going on and, a friend hasn't said something for a while, you might sort of say, oh, well, what do you think about this? And so someone who hasn't had access to the shared channel for a while, you give them sort of priority to see if they have something that they've wanted to share but haven't been able to get a word in edgewise. And, it's interesting, as we look at MAC protocols, we can kind of go back to this notion of having a conversation and really use it to sort of understand at an intuitive level how MAC protocols really work. And so, again, because the wireless channel is really kind of the main event for us these days in terms of direct shared channels, we're going to talk about that a fair bit. However, we will still, discuss Ethernet both in kind of a historical context and a modern context as well. Now, when talking about MAC algorithms, we can kind of divide them into families in a couple of ways. And the way that I like to think of MAC algorithms is kind of asking two questions about them, or sort of putting them into two broad categories. The first category is algorithms that use the dynamic or the static access approach. And then the second is, does the algorithm use a centralized or decentralized approach to its control of the shared channel? And so let's talk about dynamic versus static access first. So static access is when the shared channel is divided into static pieces that are dedicated to individual nodes. So for example, if we were in a classroom and I was teaching maybe to a group of 10 students, one way that we could decide to divide up the shared audio channel is for everybody in the room to get 20 seconds to use the shared channel. And we would just sort of go in a round robin style where we take turns. So I would speak for 20 seconds, then the first student would get 20 seconds, the second student would get 20 seconds, and so on. Then eventually it would come back to me. Now, you can imagine in a classroom setting that this wouldn't be a very good way to divide the shared channel because, generally speaking, the instructor has a lot to say and the students want to hear what the instructor has to say because you want to learn something from the instructor. And so giving, a huge portion of time to, the students in the class would be wasteful. And in fact, many of the students might not have anything to say at all. And so they would just their 20 seconds would pass without any use of the shared channel. So that's static access. The second way we can sort of manage access to the shared channel is dynamically. And with dynamic access, nodes access the channel as required. And in the classroom example, this makes a lot more sense. So as the instructor, I would be talking probably a lot on the shared channel. And when students have questions, that is when they would try to access the shared channel, either by, just saying the question out loud when there was a gap in what I was saying, or perhaps by putting up their hands to indicate that they were requesting access to the shared channel. And it seems like, using that example, dynamic channel access just seems so much better. It just seems obviously better. And for most internet-style communications, dynamic access of the shared channel is what is the approach that we use. So internet traffic is very random and very bursty. So if you have a bunch of devices on a Wi-Fi network, for example, maybe one person is browsing a web page, so they might send a request for a website over the channel. Then they might download a burst of information to get that web information onto their device, and then they would have no traffic at all for a while the person just sat there and read the web page and decided on which link to click next. Game traffic would be bursty. Even video traffic is bursty when it's compressed because, sequences in the video where there's a lot of movement, like, an action sequence in a movie or a sporting event where there's a lot of player movement on the screen, requires a lot of throughput, a lot of bits. But then when the scene in the video settles down, so for example, maybe when we're interviewing a player between periods in a hockey game, the bit rate really drops because there's not a lot changing from frame to frame. And so internet is random, it's bursty, and so this dynamic style of channel access makes a lot of sense. But, I want to also make a pitch for the benefit of static channel access. So in the interest of full disclosure, this class is largely about the internet, and I will be taking a very internet-centric approach to talking about network design. And so internet is definitely based on dynamic access. And so when you kind of finish this course, you might be tempted to think, well, dynamic access is always better. But that's not necessarily the case, particularly for engineers working with networks. So one common engineering application of networks is for instrumentation and control in an industrial facility, maybe a manufacturing facility or, an oil and gas refinery, if we think about sort of Alberta's context. And in that kind of situation where you maybe have a bunch of closed loop control systems running, it is very important to sample all of your instruments regularly and perhaps take action very regularly as well. And so in that kind of industrial setting, a static access situation or a static access approach might make a lot more sense, because you know that everybody, all the nodes on your network basically have the same amount of information to send. And a lot of control systems require very sort of predictable kind of network performance and information delivery in order to maintain stability. So just not to, and I'll try to make this point as often as I can. The next way that we can sort of classify Mac algorithms is whether they used a centralized or a decentralized approach to controlling access to the shared channel. So centralized control, as the name suggests, is when a single controller node decides when a node can transmit. So we sort of have a master node that all the other nodes have to, sort of defer to when trying to access the shared channel. This is probably a pretty good model for the classroom, right? So when an instructor is lecturing in the classroom, the instructor's talking away, and typically when a student has a question, the student will raise their hand, and that is basically, the student node requesting that the instructor node grant access to the shared channel. Decentralized control is when nodes kind of sort out among themselves who can transmit. And this is a lot more similar to a regular conversation between friends. So when you're sitting around with a group of friends, you don't really have one person, unless that person is very overbearing, you don't really have one person controlling the shared channel. You just kind of, everybody's sort of talking on kind of an equal footing, and you use rules like, don't interrupt, wait till the other person is finished in order to manage access to the shared channel. Not surprisingly, decentralized control is the philosophy used most commonly with internet communications. And so really one of the whole philosophies behind internet design, dating all the way back to ARPANET, when we wanted to make networks that were robust to nuclear strikes, the philosophy has very much been to embrace the notion of decentralized control. Rather than having one sort of master device mitigating or arbitrating access, let all the nodes figure it out for themselves. And so it makes it very easy to add a node, and it also makes it not a terribly big deal if a node just sort of disappears. Not only did this make ARPANET robust to attack, but it also, as it sort of evolved into the commercial internet, made it very easy to scale and modify the internet. So decentralized control allows us to add a node to a network whenever we want, take away a node from the network whenever we want, and not have to sort of worry about updating some sort of centralized authority. So we're going to talk a lot about decentralized control, but again, I'm not trying to make the case that centralized control is just always terrible. So for example, again, going back to our kind of industrial instrumentation network scenario, centralized control often makes a lot of sense. So if you've got, let's say, a manufacturing facility where you've got a bunch of robot arms, or a refinery where you've got a bunch of sort of fixed chemical processes, it makes sense that one device would know the entire topology of your network, because that's how manufacturing facilities are planned, right? You need to have a full plan of your factory. And it's very important to have a highly reliable, highly predictable network. Decentralized control is great, but when nodes are kind of figuring things out for themselves, sometimes one node can interfere with another node, sometimes the delay through the network is a little uncertain. And if you want to just guarantee very reliable, stable access to a network, again, if you're trying to implement control loops for chemical processes or something like that, it makes a lot of sense to have centralized control. So if you do end up having a career in industrial network design, you'll see standards like wireless HART, 802.11a, where centralized control actually is used for wireless networks. So again, we're going to talk a lot about dynamic access. We're going to talk a lot about decentralized control, but don't forget that static access and centralized control does have its place. And finally, the last general concept I want to introduce at this point is the notion of channelization. And when you have a shared channel and you want multiple nodes to use it, you have to divide it amongst those nodes somehow. And channelization is basically just refers to taking a single high throughput shared channel and somehow dividing it into several sort of lower rate parallel channels that can be shared among users. And so often when we talk about dividing a channel, we're talking about a multiple access scheme. And so one way that we can divide our shared channel is by chopping it up in the frequency domain. This is known as frequency division multiple access, FDMA, or more commonly these days with modern cellular standards and modern Wi-Fi standards, we chop a channel up in frequencies using a technique called orthogonal frequency division multiple access, or OFDMA. But they're the same concept. Essentially, we take the shared channel in the frequency domain and we chop it up and we give one range of frequencies to user number 1, another range of frequencies to user number 2, and a third range to user number 3. So this is done in cellular telephone systems. This is done in those family band radios that people sometimes use on the ski hill. It was done with old CB radios as well. The second big type of channelization or multiple access scheme is time division multiple access, where we just take our shared channel and we chop it up into time slots in the time domain. This is time division multiple access, or TDMA. And this is essentially just taking turns, right? So TDMA is how we divide up the audio channel when having a conversation. I get the channel for a little while, somebody else gets the channel for a little while. And TDMA is used very commonly for internet communication. So for example, Wi-Fi communication uses TDMA. So different nodes will transmit at different times over the shared channel. Ethernet is based on TDMA and so on. However, it's also common for us to see kind of a mix of channelization techniques. So again, taking the Wi-Fi example, it is possible actually to designate different frequency channels for Wi-Fi transmission. And then within each of those frequency channels, multiple nodes will share that particular frequency channel using TDMA. So you can take 10 nodes and say use this particular channel. Those 10 nodes will then tune into that channel and use TDMA to share access to it.